Okay, good afternoon everyone. I will get going so that you can get to drinks and the prizes shortly after this. So, title of my presentation, In-Memory Computing, It's New and It's Not. We have been doing using in-memory techniques for a large number of years, and that's the gist of the presentation I'm going to give. My title is Chief Product Officer. I get asked this a lot, what is a Chief Product Officer? The way we view it is there are three things that are really important to the company. Finances are very important, so we have a Chief Financial Officer. Customers are very important, so we have a Chief Customer Officer. And products are very important, so we have a Chief Product Officer, and that's where I fit in. We actually have one of our founders of the company in the front here, Bill. He obviously thinks executives are very important too, because he appointed a Chief Executive Officer. So who's Data Kinetics? Anyone in this room other than Bill ever heard of Data Kinetics before? Yeah, I didn't think so. So we've done a really good job of not telling anyone about us. We are actually just past our 40-year anniversary. And in that 40 years, we've been solving IT problems for some of the largest companies in the world. We do have 3 of the top 5 global banks as our customer, 3 of the top 5 global credit card companies, 3 of the top US property and casualty insurance, and 2 of the top US health insurance companies as our customer. We represent a significant chunk of the Fortune 50. So we've been doing a lot for that 40 years, except telling everyone about what we're doing. So part of the reason I'm here is maybe there'll be 12, 15 more people that know who Data Kinetics is. So why am I presenting here today? As I said, we've been using in-memory techniques to accelerate processing for 40 years. There's 2 products that I'd like to mention, and I will put a slide up for each one of them at some point, and I recognize that as a blatant product pitch, but I'm okay with that because in most of the other presentations I've been in, there's been blatant product pitches as well. So we have 2 products that fit in this in-memory space. One is a product called TABLEBASE, which we refer to as an in-memory accelerator, and that's the 40-year-old product. We also have a data replication product that does a lot of change data capture and replication, primarily off the mainframe to distributed systems, and that's very relevant for some of the talks I've heard about, seen today, where there is a need to get that system of record data off the mainframe and into these distributed data systems to do analytics or other processing. There have been a lot of changes over those last 40 years, although we think some things are relevant still today because we still have to convince our customers they're relevant today. So we're spending a lot of time on that as we move forward. So I did mention the name mainframe. We have been a mainframe company for that 40 years. We do play in other spaces, but mostly in the mainframe. So is it still relevant? I get asked this a lot. When I took my current job, which was 6 years ago, people said, "Are you nuts going into the mainframe business?" Well, maybe, but we're doing all right. So mainframe is still used by 92% of the top 100 banks. Almost 100% of credit card processing is done by mainframes. And there's a good chance if you used a credit card today, your processing touched our software along the way. There are many other statistics up there that I won't simply read through. But the point is the mainframe is still relevant. There are workloads that probably don't fit on the mainframe, and I know I've seen a lot of the discussions today in various presentations talking about loads that fit very well on in-memory computing, which is probably true, that maybe historically have fit on the mainframe and maybe need to move off the mainframe moving forward. So why is in-memory considered on the mainframe? We spend a lot of time talking with our customers and potential customers, obviously, and it's nearly always about the dollars. If an accountant's not going to be happy at the end of the day, nothing's going to happen, right? So we come into that time and time again. However, when we look deeper into the rationale that we're working on with our customers on, it's normally one of the 3 following things. They're either looking to improve response time, reduce elapsed time, or reduce the CPU usage. And these 3 things overlap. If I reduce the elapsed time, it's a similar thing to improving the response time. And if I reduce my CPU usage, I'm likely to be reducing the other 2 as well. However, we do know that improved response times is normally related to SLAs. Customers are violating their SLAs, which is costing them money, or they're unable to do enough work to detect fraud, in which case they're losing money. So those are the challenges with an improved response time. Reduced elapsed time is normally a throughput type issue. How do I get my batch window to run in the 8 hours that I want it to run in overnight? Because if I can't do that, I'm running into my online window the next day and I've got a different problem, right? The last one, and it's probably the one we spend more time with on customers today than historically have done, is to reduce the CPU usage. The reason for that is, on the mainframe in particular, the software is priced based on how much CPU you use. In many cases, our customers have what they call a MLC license, so a monthly license recurring charge, and the amount is dictated by their peak usage for the month. And the peak usage is defined as the rolling 4-hour average peak. So we have a lot of customers that are very eager to reduce their CPU usage because the second they do, their monthly recurring bill that they pay to IBM and potentially other vendors will go down. So reducing that CPU usage becomes key, and this is one of the areas where we've been working on a lot lately with our customers to help reduce their monthly bills. So there's two reasons that we're using the in-memory generally. One is to reduce I/O wait times. So this is the time when you have to go out to the disk and fetch the data and come back. Obviously, if the data is in memory, this can be done faster. So reducing the I/O wait times definitely will improve the response time, and it'll definitely improve their elapsed time. But moving data simply from disk to memory doesn't necessarily do a lot to change the CPU. The second thing you can do is not only reduce those two, reduce the I/O wait times, but to reduce the code path. So this literally means the number of machine cycles I need or number of machine instructions I need to execute in order to retrieve data, as an example. So this one impacts all areas, improves response time, reduces elapsed time, and reduces CPU usage. And since most of the time we spend working with our customers on how to reduce CPU usage, it's that second one we have to work on. We have to look at how do we reduce that code path in order to reduce the number of machine cycles used, which does improve things across the board, but generally they're looking to reduce CPU usage. Not to say there aren't others. There are a lot of technologies, and I'm not even going to go into all of them, where I/O has been reduced on the mainframe. Not dissimilar to what you might see on other systems. Caching is used, buffering, which is like caching within the products. So DB2 uses buffer pools to cache the data that it's reading off disk to avoid needing to go back to the disk. The other part about the buffering is generally when you're reading from disk, you read a block. So you read that whole, even though you only might need a portion of the block, you actually keep the rest of that block in memory, as there's a high likelihood that the next retrieval is going to be the next block of the next part of the data, which is in that same block. And there's third-party tools that do this. VSAM, which is another record structure on the mainframe, also has buffering mechanisms as well. And in some cases, they're buffering the index. In some cases, they're buffering the entire row of data. CICS manage data tables. So CICS is an online system, transactional system. So it has managed data tables, which it can manage in memory as a way to improve response times by removing that I/O. COBOL has internal tables, which you can generate and keep the data within the memory of the program, and et cetera, et cetera. All of these reduce I/O, and when we're working with our customers, we're encouraging them to do this. However, what we bring to market is a product called TABLEBASE. So it's an in-memory table manager. It helps manage the tables in memory, and it does it at a reduced code path compared to equivalent functionality on the mainframe. It not only removes the I/O, it reduces the code path. So here's performance results against a common mainframe database between TABLEBASE and this database. You can see that on multiple different measures, TABLEBASE is much faster. Now, this was looking at the performance after the database had been optimized. And the way they optimized it was they put the entire row in the index. By putting the entire row in the index, it got locked into the buffering mechanism. So this was a fair comparison of memory in data, both in the database system and in TABLEBASE. And as I said, TABLEBASE has been optimized purely to reduce that code path. And as a case, it's much faster. So what we see is we see this getting used a lot by our customers, and we work with our customers a lot on identifying areas in their computational systems where they can use this to improve performance. It gets used primarily in two ways. One is to hold what we call reference data. So this is, I'll actually talk about reference data a bit more later on. And the other one is temporary data. So data where you're collecting results and you need to search on it multiple times. And again, I'll give an example of that later in lessons learned. The other product that we have that's in this space, and I added this slide literally a couple of hours ago when I realized it might be relevant to this audience. So we have a product that does data replication. It replicates the change data, and it can replicate that change data to any targeted system, typically in a sub-second way off the mainframe. This product grew up in the mainframe space. It understands the IMS and the DB2s and the VSAMs of the world, which are the predominant data stores on the mainframe. And it's able to replicate that off using a publish-subscribe mechanism to guarantee delivery. It does this all in memory. If you give it enough memory and you don't lose your targets, if you don't lose connectivity to your targets, it does everything in memory. If it loses connectivity to a target, it will eventually run out of the memory you've allocated to it, at which time it will start to persist to disk and things do start to slow down at that point. Doesn't require any staging of the data. It can go directly out, and most of our recent projects using this product have been to take that mainframe data and push it out through a Kafka queue for obvious reasons, in that the Kafka queue is being used to feed various data grids, etc. So that's it for the product pitches, by the way. So we've learned a few things along the way. Some of it, most of these things, as I said, we have to keep on going back to our customers and reminding them that we have learned this stuff and they don't need to relearn it again. It's surprising how often these problems come up again. So I'm going to go through which data, why indexing is important, and give some specific examples of those. Not all hashes are created equal, which is a problem we've seen in very specific circumstances. Rules, separate out the read-only, and then the accusations. We get a couple of very common accusations because we change the way they're processing. We get accused of things that maybe aren't true. So which data? What to put in memory? So you put big or small transactional data into memory, and I am focusing on transactional systems at the moment. So large data takes a long time to search. So putting it in memory can drastically reduce the I/O. So it can give you a great response time improvement. It can give you a great elapsed time improvement. What we have found in the systems we've worked at closely is the CPU impact, the amount of machine cycles required for this impact is normally minimal. And I'll explain why that is on the next chart. Small data, this is data small in size, accessed very frequently, often referred to as reference data, typically will give a good response time improvement. Not a great response time improvement, but a good response time improvement. Similarly, it will give a good elapsed time improvement. However, if you do it effectively, the CPU impact on moving that small data to memory can be huge, right? So to give you an example, here's a batch job that happens to run that has 3 different tables. One table has a record for every transaction that occurred on the previous day. And in this case, we're talking about 10 million rows. We're assuming 10 million rows. We do have systems that are running 2 billion rows, but let's talk with the 10 billion row example. We have a product table that is referenced by this large table, which has about 200 rows. And then product in this case is actually a credit card product, so 200 different types of credit cards. And there's another table that's accessed, which is tax region table, which has 5,000 rows. And I'm just making this up, by the way. I don't think of a specific example where this occurs. So if you read that large table into memory, you will improve response time, but you have to have spent the CPU cycles in order to read that into memory for the times you're going to access it. And typically when you're running a batch job against a table like this, you're going to read each row once. So you've taken the effort to read each row into memory once, and then you're going to access it once. You haven't gained anything. You really haven't gained any CPU gains there. That's much different for the smaller tables. So the top table, which only has 200 rows, each row is going to be averaged on average 50,000 times. So the effort to read it into memory is definitely worthwhile. I get 50,000 times the return of whatever I gain by doing so. So that's very valuable. And obviously the second table, it's a 2,000. So we spend a lot of time with our customers working on, well, which tables? And they'll come to me and say, well, I've got this 300 gigabyte table, and that's clearly my problem. And we say, well, have you looked at what other tables are accessed during that same batch processing window or during that online transaction? And more often than not, it's, well, yeah, there's dozens of other tables that are accessed at the same time, but my big table is my problem. And we're able to walk through with those customers and explain to them, well, if we move the smaller data into memory, you're not going to have to go and increase the memory size of your computer, and you can get huge advantages of it. Sometimes so great that they don't ever consider moving that big table into memory. Again, our customers typically are focused on CPU reduction. This will help in terms of response time, but if you really want to go after the response time, you have to put the whole thing in memory. So some results from a particular credit card processor. They had a reconciliation batch job that was stretching their batch window. It was taking over 8 hours to run, and they typically only have an 8-hour batch window. So this was a reconciliation, so it looked like the previous chart. They actually had several tables that described the different cards and how to process the transactions for the cards. And they had one very long transaction table that was actually the transactions that occurred. We moved those tables into TABLEBASE. We then repeated the run, and we saw a 97% reduction in CPU. That batch job that took over 8 hours to complete now ran in 15 minutes. We instantly got complaints because the managers got their report late the night before, and they'd never seen a report late night before. They'd always seen it the morning after. So they instantly assumed there was something wrong with the system. So as I said, there's a number of different ways to do it, but from an economic perspective in the customers we're working with, moving that small data into memory can give a reduced cost. Moving large tables into memory can certainly be cost neutral, potentially more expensive because of the memory requirements. But if you're going after that response time improvement or elapsed time improvement, you would consider that. If you're purely looking at the cost and you don't want to have a huge increase in your memory requirements, then moving that small data into memory can have a huge impact. Next one is indexing is important. This sounds kind of obvious, but it is something we have to remind our customers from time to time. So one of the technologies that you've probably heard a bit about when you heard about the dinosaurs and the mainframe is a language called COBOL. So COBOL has a thing called internal tables, which puts data in memory. And there are many things that can help by putting stuff in memory. And it's often used to manage temporary tables. The problem with COBOL internal tables is they don't have the concept of an alternate index. So COBOL tables generate one index, a primary index, and if you want to search by some other criteria on that table, you now have to worry about either reloading the table again, which is possible, or you need to just do a serial search until you find the element you're looking for. So one of our former employees actually went to work for a bank, and he identified this and said, well, I can do much better because I know how TABLEBASE works. So he took a COBOL program that was using an internal program. It was searched 1.25 million times, which in itself isn't a huge issue. The issue was it needed to do 4 different searches, and you could only put one primary index on that table. So the solution was to put this in TABLEBASE, let TABLEBASE build the index on the fly for the 4 different searches, and then repeat the process. And that job that used to take over an hour to execute, executed in less than a minute. And he didn't bother to tell us about that for 15 years. So it's nice of him, but we actually know about it now, so it was kind of good. So which index to use? A lot of the indexes we're using is on fairly straightforward keys. And when you're indexing for speed, we find that if it's less than 10 rows, serial searches is typically the fastest. Between 10 and 100 rows, we typically switch to a binary search. And if it's greater than 100 rows, we're looking at a hash search. I'm not sure how other technologies play out, but they're probably along those lines. And when we talk about a hash search, we're talking about a very specific hash index, and I'll actually talk about that next. And the reason I'll talk about that next is we discovered that not all hashes are created equal. So it's important to look at what a hash does. So what does a hash do? It's basically mapping one address space to another address space. Sorry, one space to another space. It's a one-way, normally a one-way action. You can get 2 ways, but normally it's one way. It's typically going to shrink. So it's going to take a very large space and shrink it to a smaller space, although it doesn't have to. It can take something of arbitrary length and make it a fixed length. It can also encrypt. It can also, so it's used, hashes are used in a large number of ways. When we use it as an index, we use it in a very specific way. So when we use hashes in an index, we use it to calculate a slot, right? So an index, if you've got 1,000 rows in the table, we may create 2,000 slots, and then our hash function will map every key. So, I've got to get over here. Yeah, so map every possible key to a set of memory slots is how we do it. And then we can do direct calculation on those memory slots, and it becomes very fast to do a search when we do that. The challenges with this are we don't want to use an infinite amount of memory to create those slots, so we have to restrict it down to a certain size. The smaller we make the size, the better we are with memory usage. However, the worse we are in terms of collisions. So we talk about densities. So density is the number of keys divided by the number of slots. So if I got a 50% density and I'm inserting a new element, I got a 50% chance of getting a collision if everything's considered equal. So the higher the density, the less memory I use, but the more likelihood I'm going to get a collision. And every time I get a collision, I need to do special processing to deal with that collision. If I get a lower value, I use more memory, which is good, but I end up with, I use more memory, which is bad, but I end up with fewer collisions, which is good, because it takes me less time to process it. So we took our hash algorithm, which we thought was pretty good, and then a customer had a particular key set that they said, well, your key's not working that well. Sorry, your hash algorithm is not working that well. So we went and studied it, and we looked at our collisions by key for our hash algorithm going up to 10 million rows. And 10 million was quite specific because the customer needed 9 million rows in their table. We thought, oh, this is pretty good. We've got a fairly cheap to calculate hash, and we're not getting many collisions per key, so this is really good. The yellow line there is actually the ideal, and the red is our calculations to what ours was, right? Obviously, there's room for error since we actually dropped the low ideal for a big chunk of the time. The jerkiness of the line is because at various points you have to keep on extending the size of the number of slots, because obviously if you've got 1,000 keys, you don't need 1,000 slots. But you need only need 1,000 or 2,000 slots. But when you get up around that 9 million number, you need a much bigger chunk of memory. So that's why we get that error, what appears to be a lot of errors on the lines. However, we then plugged in the customer's key structure that they gave us. It was actually a customer that did trading, and the key was basically a combination of the trading index and the date the stock was issued. So each stock has multiple issue dates for their stock, and so each each trading key had a date attached to it. And when we put that through the same testing, we saw that the collisions on our hash algorithm went drastically above the ideal scenario, which is the green line at the bottom, and you can see the red. Huge amount of collisions. And then on the right-hand side is the impact this had on the CPU. Because we had so many collisions, we had to do extra processing to find another slot. If that also resulted in collision, we had to find another slot. If that also resulted in collision, we had to find another slot. So as the collisions climb, so did the CPU usage. That yellow line on the second one is the performance we eventually found on the best hash algorithm we could find. So you can see, even at the low end, when you didn't have many keys, our hash algorithm was pretty good. It was cheap. It was much cheaper to calculate, and it could afford a certain level of collisions before it became more expensive. However, when you get to the latter part there, the collision rate was just killing the computations. So when we discovered that our algorithm didn't work so well, we went and studied a bunch of others. And you can see different algorithms gave us different results. The best one performing at the really high level is the red line, which is called F on this thing, and it was so good in the collisions to key that it actually falls below the ideal line, which is why you can't see it. The yellow line's actually overlapping the red line in its entirety. So we could see that even though it made at lower indexes, it might have not been the most optimal computationally. When you certainly got up into those large tables, it certainly was far more better performer. So where does this leave us? If we don't know much, so we don't know how big the table's going to get, and we don't know anything about the key, you want something that's going to completely randomize that key distribution, and as a result, avoid those collisions. And the one that performed the best, as far as we could tell, was a fail and null though hash algorithm, or FNV algorithm. So that's, if you do a search on that, that's readily available out there. But if we know something more about it, we might use a cheaper to use hash algorithm. If it's a well-distributed key, you don't have to throw as much randomness in it. If it has a small number of keys, you don't have to do a bunch of calculations to take into account that I could end up with a big table. And the last thing is, if we know we've got a very low density, we may then use that much cheaper to calculate hash function. So give some example of some keys that might become relevant. So I live in Canada, although I've got an Australian accent, I live in Canada. So in Canada, the postcodes go letter, number, letter, number, letter, number. So you end up with 6 bytes substantially. And if you were to look at those 6 bytes, you've basically got, 300 billion possible combinations for a Canadian postcode. However, there aren't that many places in Canada, so they don't need 300 billion ones. So it turns out they don't use the letters D, F, I, O, and Q, or U. And this is because something about confusion between different letters when it's handwritten. The letters W and Z are never used in the first position. And there's also, there are occasionally restrictions on the numbers. So we can actually, by taking into account those letters and the fact that it goes letter, number, rather than just looking at the bytes, we can bring that down to 7.4 million possible combinations. So the table that I'm dealing with is now substantially smaller. My largest possible table is now substantially smaller than what it could have been. And actually, it turns out only about 10% of those are in use. And again, there aren't that many people in Canada, so that makes sense. Was it about 33 million people? So that's how many postcodes are on. So it is worth talking briefly about the standard hash. So the standard hash out there that often gets used on Linux, there's a 32 and a 64-bit algorithm, and that's the formula for it there. And if you invoke a hash algorithm without thinking too much about it on a Linux system, this is the one that's going to be applied. it maps any string to either a 32-bit or a 64-bit number. It actually turns out if you take this to high density, this is not a good performing hash algorithm. Your collision rate will skyrocket. However, because 2 to the 32 and 2 to the 64 are such big spaces, unless you've got really, really massive tables, you don't need to worry about it. And that's why the hash algorithms that are often used in the various hash distribution mechanisms or sharding methods work, and that's because you've got those very low collisions. But they're not actually being used to calculate a slot, they're actually being used to calculate an order, which is different from calculating the slot, which is how we use the hash algorithm. One thing we've learnt over the years is rules, rules, rules. The most frequently read tables that we come across with our customers tend to be rules. They don't tell us they're rules, but when they give us a description of the table, normally there's this rule in the name of the table. So we generally conclude that this is a rules table, and we discover that they're very frequently read. I had a customer sent me data on statistics of table reads, and there was one that stood out from all the others. It was read 20,000 times a second, where there wasn't another table that was read more than 2,000 times a second. And that table that was read 20,000 times a second had rule in its title, so I knew exactly what they were doing. So why rules processing? So business rules are among the organization's most valuable intellectual property. How do I process my transactions? How do I detect fraud? How do I manage my products? For speed of processing, business rules are often encapsulated in the code, right? Those customers that don't like everything encapsulated in the code extract those rules and put them in tables. And this gives them a lot of flexibility. It's much easier to change a rule if it's in a table than it is if it's in code. So for flexibility reasons, customers generally will often put these decision criteria into data. And actually have a chat with Bill afterwards about the rules, the table-driven rules processing he's worked on in the past. So what we find is that when these rule tables get read, they often get read hundreds of times more often than other tables. So fraud detection rules often are a good example. Fraud detection often looks for multiple criteria that could be met by an inbound transaction. And if it's met, you've obviously got a fraud condition. So these can be hundreds of rows. So you may have thousands of rows in the fraud rules tables, but you may end up needing to read hundreds of them in order to do a reasonable job of fraud detection. So as I said, we keep on seeing rules tables show up as high runners. And what we found is obviously by moving those into in-memory solutions or in-memory tables, we can access them far faster and reduce the runtime of the applications. If you can separate out read-only data, and often people can't, but if you can, we've seen even more efficient solutions for our customers where data can be treated as read-only. And we have customers that will do things like they will unload tables every hour and say, well, they're read-only for the next hour. They may change, but I'm okay with them being updated an hour later. And that's to get these performance gains that I'm going to talk about next. So where you've got shared memory tables, so where multiple applications are going to actually access that same set of data, not almost simultaneously, you need a set of routines to deal with how to clean things up when you have failures. So many data access algorithms use locks or similar to control when data can be updated and when it can be read, to make sure that you get a consistent set of data out to the reading applications. Locks are a very common mechanism. There are other mechanisms. And any lock, if there's a failure of a program, often you need to make sure you can remove that lock, or else that lock stays indefinitely and programs aren't able to do their jobs. And what we've found is that this can be 60 to 85% of the code path, is just to put mechanisms in place to make sure you can remove those locks. So if you've got read-only data, you can put it into an application and say, don't worry about locks, just let the data be read. And then I can reduce my code path even further. And again, where code path has a direct impact on cost, that can be very valuable. So by separating read-only data, we can remove all the locks. We might see a 3 to 4 times improvement. The other approach is if the data is only updated rarely, you can assume that it's not going to change, and then you just put a counter in there. And every time the data changes, you update the counter. And the way this works is an application uses the data, and if the counter changes while they're using the data, they say, oh, that was probably a bad read. I've now got to deal with the fact that that was probably a bad read. We've also built for a customer a switching mechanism where they could have a set of tables that were active and they'd build another set of tables, and then we provided them a switch where they switched to the new set of tables, so that every transaction that was using the old set of tables would continue to use the old set of tables, and our switch mechanism meant any new transactions would come into the new tables. And again, this was to get around this. If I'm really looking to gain that CPU performance, I might try and start playing tricks like that. So now, let the accusations fly. This is one of those ones where we help a customer improve their programs, and then they turn around and start accusing us of stuff because things have changed in their system, and since we were the last ones in, clearly it's our fault. So 2 of the most common things that get happen. One is you're using all the CPU. Didn't you just say that you could help us reduce our CPU usage, and now you're using it all? So what's normally happened when we get accused of using all the CPU, we've removed all the I/O weight from a program. When we remove all the I/O weight, it never stops. It never stops and lets other programs run in order to go and get data. So it just runs continuously. And when it's running continuously, it looks like it's using all the CPU. That 8-hour batch job that I told you before that took 8 hours to run and reduced to 15 minutes, for that 15 minutes, it was probably peaking at a much higher CPU than it had used for the entire 8 hours. But overall, the amount of CPU used overall was drastically reduced. So you could run that job at a lower priority, or you could just say, hey, for that 15 minutes, it gets to run, and then I get my computer back to run everything else I want to later on. So that was one of the accusations we've seen. The other one is you are using all the memory. Don't hear this one much anymore because the cost of memory is coming down, so people are adding more memory to the machines. But back when people were trying to maximize every single bit of memory they were using, and the memory mechanism came out where we could actually swap memory in and out to disk. Because we let our applications run so fast, they were accessing the data in the memory that we were using frequently. When you're accessing the memory frequently, it never gets paged out in the mainframe. They call it paging out. When paging out that portion of memory. So it looked like our applications were hogging the memory. And well, they kind of were, because they were reading the memory so frequently, they were never letting another program bring a page out of disk into memory to use that slot of memory. So it looked like we were doing it. But again, the same argument applies. But if we're doing it, we're only doing it for a very short period of time. So it's not so bad. So those were the accusations we normally saw. So in conclusion, thank you for your time. If I did this again, I'd probably pick a different set of examples we've learned over the 40 years, but I tried to pick stuff that was relevant to what I thought the audience was going to be interested in. So in conclusion, the mainframe is still relevant. Yes, I know workloads are moving off the mainframe on a regular basis, but we've done quite well out of the mainframe, and we probably will for a while until everything's moved off the mainframe. In-memory can help on multiple fronts. I've certainly heard many examples today where in-memory can help, and we're certainly aware of that from our background. One thing we do know is if it doesn't have a business case, there's no point in even talking about in-memory. Just because it's fast and neat doesn't necessarily make it better unless somebody is making more money along the way. Particularly on the mainframe, the small data putting in memory has a bigger impact on dollars. Indexing, including using appropriate hash function, is very essential. Rule tables are often the most read, and careful what you wish for. So thank you. I think we've got question and answers now. So.
If you've got a question, let me know. Ask you the microphone, and that way everybody can benefit from your question.
So how much changes are we looking at in the mainframe programs with this?
Changes?
Yeah.
Well, I'll give you a good IBM answer to that one. It depends. Our analysis says typically less than 1% of the code base in the applications being impacted. Typically. I can certainly find examples where it's not, but yeah, typically 1%. So.
Is there still a market for COBOL?
Still a market for?
COBOL.
Yes, there is. If you know any COBOL programmers, they're pretty much guaranteed work at the moment. So.
Anything else that old that's still working around?
That would be the older stuff, without a doubt. There is a lot of Java ending up on the mainframe now. A lot of the workloads that were in COBOL are being migrated to Java or others. Our stuff is written in assembler, which probably predates the COBOL stuff, although modern C compilers would be the choice there now. So.
Why are you using assembler?
So the product's 40 years old. It was written in assembler for speed originally. If we were to write it, the main portions, if we were to write them today, we'd be writing them in C. Okay, doesn't look like there's any more questions, so you've got a few minutes before the drinks open. So, thank you.